All right, so let's talk about the Gini index. The Gini index is actually kind of cool when you think about it. So this is 6.2. Yeah. Okay, so the Gini index is actually kind of cool when you think about it because it gives you a way of measuring how evenly income is distributed across a society. Because that's something we're talking about today a lot, right? Everyone's talking about income distribution, how the top 1% has everything. What's the cutoff for the top 1% in most states? What would you think?
Like salary range?
Salary, yeah, income. What's
What's
that?
There is a max.
No, not a max, the cutoff. What starts the 1%?
Like 350,000.
Yeah, it's 350, did I say that on the video?
Oh, yeah.
Okay. Most people think, oh, it's like $1 million. It's actually not. A busy surgeon puts themselves in the top 1% if they're making about that. So it's not all the Bill Gates. Within the top 1%, there's this huge distribution as well. There are a few Bill Gates and then a whole lot of people who are making 300 or 500. So the Gini index is cool. What it starts with, it starts with a Lorentz curve. And so what this is going across is this is the percentile of people. So this is people going this way and income going this way. And this is a cumulative graph, which means that by the time you get to 100%, and we do whenever we're working in math, when we're computing things, we always use the decimal. So this is 100% of people. Once we get there, we should be at 100% of the income, right? Because everybody has everything. And when we start down here with no one, we should have none of the income. So ideally, if this is uniformly distributed, right, then 50% of the people will have 50% of the income. The bottom 25% of the people will have the bottom 25% of the income. And so that would be ideal. Well, some people would say ideal. So then the question becomes, what does our society really look like? Yes?
So you said ideal is when it's closest to zero, to the...
Well, when you're closest to this line. So this line is the income distribution line. Hang tight. We're gonna get to what you're alluding to. So if you have a straight line, it says that each percentile of people has exactly that percent of the income. So that would be considered an even distribution. Everybody has kind of the same amount. In reality, we know that these people out here really have more of the income. And so in reality, we look probably more like that. So coming down here, the bottom 25% of the people might have 10% of the money. And when we get over here to 80%, they may have a lot more. And so it could be even worse, right? The squarer it gets like that, the more it says that the people down here don't have so much, and then all of a sudden everybody has the top people have everything. So given that this is what we're looking at, the Gini index puts a number on that. And so what the Gini index is saying, let's just consider one curve, what the Gini index is saying is if I could figure out kind of this area, then that gives me an idea of how far off I am from this straight line that I would like to be at. So the bigger this area gets, that means the further away the curve is and the less equal I am, the less equal the society is. So if we're aiming for the straight line, and this is what we really have, well, we know how to find area between two curves, right? This one is y equals x. Because at 0.5, it's 0.5, at 1, it's 1. This is a straight line, slope 1, intercept 0. So if I want to find the area between those two curves, I'm going from nobody to everybody, 0 to 1. Top curve, and if it helps you, start on the top curve, draw an arrow down to the bottom curve. Top curve, bottom curve. So this bottom curve we call the Lorentz curve, we'll just call it f of x. But if you were to think about what the maximum number would be here, right, if it were worst case scenario, you hug this x-axis all the way till you got to the end, so one person in the society had absolutely all the income, you would have a triangle, and the area of that triangle would be a half. Somebody along the line said, wouldn't it be nice if the max were 1 instead of a half? So they just threw an extra 2 in there. That's just the definite, this does not come from the area, this comes from somebody defining this thing called the Gini index, and they put a 2 in there because it makes the numbers nicer. That's all that is. So, no, really. Well,
I know, but it's just nice to know that we can just throw numbers around like that.
Well, you can throw numbers if you're trying to scale an index. So the index is not strictly speaking the area. The index is a number that tops out at 1. So when you get to 1, that means you are as far, you are the whole triangle. You are completely unequal. If you're at 0, if this turns out to be 0, then that means this right on the line. So that means that 0 is total equality, and 1 is total inequality. Okay, so then the way the problems work is they give you some curves. So they might say 1939 versus 1945, before and after World War II. What did the incomes look like? And so you treat them separately. You do 1939, you plug it in, you do the math, you get a number. And you do 1945, you plug it in, you do the math, you get a number. And most of the time these Lorentz curves are power functions. So they might be x to the 2.4. So let's do that one as an example. So if this is your Lorentz curve, and you wanted to find the Gini index, and you don't have to memorize this, this is one I'll give you. So it's just 2 times the interval from 0 to 1, x minus 10. So you're really just dropping in this right into there. What do we think about this interval? Is it a basic or a chain rule?
It's a basic.
It's a basic. It's a power, and it's a power. So these end up being pretty easy integrals to do.
Mm-hmm.
So let's just look at that. Remember to take this off when you've done the integral. And remember, when you do powers, the way I think about it is you're doing the antiderivative to go back up to the original function. So that means your exponent goes up. So this would be x squared divided by x to the 3.4 divided by, and then evaluate from 0 to 1. It's a great evaluation, isn't it? Because you put 1 into a power, any power, and you get just 1, right? 1 to the anything is 1. And you put 0 in, you get 0. So this evaluates really easily as well. So this is just 1/2 minus 1 over 3.4, or whatever that ends up being. So it ends up, so the computation part here is pretty easy. But what then it tells you is, remember that the bigger that Gini index is, that means the more area you have. The more area you have, that means the farther away you are from equality. So that's kind of that. Is that enough on that one? Okay. All right, so let's look at probability density function. That's Gini index.
Oh, the difference. Wait,
Yes.
the x's disappeared because the difference.
Oh, because I plugged in.
Yeah, that's okay.
Yeah. And so I plugged in, but what's 1 squared? 1. And what's 1 to the 3/4? 1. And then this would just be 0. I did the plugging in part. Yeah. So this is just evaluated at x equals 1 and x equals 0. I just did the evaluation. All right. Okay, so let's look at probability density. Again, I know I've asked before, but how many people have taken statistics? Okay, a few. And they're starting to teach probability in middle school and high school now too, so you've seen some probability before. So we know probability is kind of the chance that something will happen. Often we do it in percents when we talk about it, 100% chance of rain or something like that. When we do it in math, we put everything into decimals, so probabilities will be in decimals. You can have discrete ones, which are like flipping a coin. You get heads or you get tails, right? There are 2 choices. Nothing else can happen. But you can also have continuous things like how long did you spend on the homework last night? Well, presumably it could go down as far as 0, but we're really hoping it doesn't. And at some point there's going to be an upper limit, but how many options are there in the middle? Right, an infinite number. If you could measure down to the microsecond or the nanosecond, whatever, it would be an infinite number of options. So those are called discontinuous. And so we're going to have something here called a probability density function. You don't really need to, the words are not so important. I just want to draw the picture for you. So probability density function. I'll start with this one. Everyone probably recognizes this one, bell-shaped curve. This governs a lot of our lives. The important thing about this is that the total area under, so the area here correlates to probability. So that's the important take-home point here. Area equals probability. So the total area, what's the highest probability you can have? Can you be more than 100% certain? No. So the highest probability is going to be 1. So that tells you that the total area under the curve equals 1. What we usually ask is, what is the probability that something, we get a number between 1 and 2? So down here on this axis here, what is the probability that we get x between two values? So if I want to know what is the probability that x is between some a and b. So remember, probability is area under the curve. So if I've got a here, b here, and I want to know what's the probability that x is between those two numbers, that means I want to go between these two numbers, area under the curve. That tells you where you need to be. So that means that this would be the integral from a to b, because that's how I'm adding up my area. And the area is going to be under this probability density function. So under all that fast. Will this ever be negative? Can you ever have a negative probability? No. So again, these integrals are always fairly easy in the sense that nothing's ever split. There are no weird intersection points. You're really just, the probability that x is between a and b means those are your limits. So if I said, what's the probability that x is greater than 5? Well, so if you said greater than 5, that tells you that 5 is where you start. So if you're looking for this example, then so you would start at 5, and how far would you go? Technically infinity, unless there's some other information that you know. F of x dx. We haven't really talked about this yet, and so we're not going to have, that may be a bad example. Let's talk about x less than 5. That would be better. X less than 5 starts at 0 for us, because typically these are business applications and x is usually a number of items or a number of years or a number of it's a count. So typically this will, for us in business, start at 0. And how high does it go? 5. So the big thing with probability is that the big issue is just picking your limits. But the limits come out of what the problem asks for. So if it says, what's the probability in the first year? 0 to 1, unless you're in months, and then it would be 0 to 12. That's the only thing. Sometimes you have to be careful watching your months and years. So again, this one's another fairly straightforward one in that you're just taking whatever probability they give you and just integrating over whatever the interval of interest is. Okay. So is that okay? I'm kind of inclined to, or do you want to do an example of one? Or is that, so it's really just doing the anti-differentiation. So I'm going to leave that one there. All right, so what I wanted to do today is, so let me just stop this so we can